You are welcome to the GMAT 41's physics class. In this physics lesson, we are going to give attention to a quantity called Young modulus. Young modulus is a constant introduced when studying the relationship between stress and strain. And this is actually an extension of Hooke's law of elasticity. Let us assume that you are given a material. That material has a cross-sectional area, say A. Now this area could be as a result of the material having length and thickness. We may have known that if you multiply length by thickness, you get area mathematically. Let us now consider that the force applied to this material produced an extension. Now, if the force produced an extension as is expected when dealing with Hooke's law of elasticity, one can actually study the relationship between the extension produced and the original length of this material. Now here we can define two quantities. One, the stress, and two, the strain. We are going to talk about tensile stress and then tensile strain. Now when you apply force on this material that has a cross-sectional area, the ratio of force to area will give you the quantity we call stress, which I say we can call it tensile stress because we have some other forms of stress like shear stress. Are you following, right? But here we're giving attention to tensile stress, or you can just call it stress, all right? Now, if we take the ratio of the extension to the original length, again, that defines another quantity called the tensile strain, or simply strain, without bothering yourself, okay? So our interest is to study the relationship between stress and strain. And here we bring in a constant known as the Young modulus. Actually, this aspect is a continuation of Hooke's law, like I said, and this is part 3 of elasticity. Are you following, right? We already dealt with part 1. We treated part 2 where we solved, exam-related questions, possible exam questions that you can be tried on when dealing with Hooke's law of elasticity, all right, the part 1. So using the concept of this stress and strain, we are going to state Hooke's law in another alternative way. With these two quantities, Hooke's law simply states that stress is directly proportional to what? Strain. As simple as that. Stress is directly proportional to what? Strain. Now mathematically, we can write that law as stress is directly proportional to what? Strain. Good. Now this is very important. Like I've always mentioned, when you are dealing with aspects of your study, science, okay, you want to have an open mind because one particular thing you study in a topic can have far-reaching effects in other aspects of science. Now let me just give you a little foreglimpse, all right? Just a preview into some areas that you can meet this Hooke's law stated as stress is directly proportional to strain. We have a quantity we call the bulk modulus. Understanding this will give you the idea of bulk modulus. In advanced physics, we deal with that. Are you following, right? So going through our advanced physics playlist, okay, for university students, undergraduates, you would meet that concept of bulk modulus. All right. Then again, there is this aspect of the study of fluid. There is this course in advanced level, okay, we call fluid mechanics. Then we study Newton's law of fluid. Newton's law of what? Fluid. Now that law is actually gotten from the knowledge of the fact that stress is directly proportional to what? Strain. Anyway, I'll be teaching that, okay, for those in advanced level, right? For now, let us focus on the main thing here. Hooke's law stated in this way that tensile stress is directly proportional to tensile strain. Now, I already established the fact that stress is equal to force over area, and then strain is equal to the extension divided by the original length. Alright, now permit me to use this symbol for stress, okay? This symbol is a Greek symbol, tau. Permit me to use it for stress. then permit me to use S for string, okay? You can use any symbol you want. Now, if that is the case, then this is going to be equal to the constant we use there. I'm going to use capital E to represent the constant, so it's going to multiply S. And that capital E is called the Young modulus. Is that okay? So this is our first equation here, where E is equal to Young modulus. So you see clearly that Young modulus, if I make it subject of the formula, is going to be stress divided by what? Strain. Do you agree with that? If I make it subject to the formula, it's going to be stress divided by what? Strain. And of course, we have it here in this format, stress divided by what? Strain. So this is the formula for Young modulus. Now I'd like us to introduce the formula for tensile stress and tensile strain. Is that okay? I already told you that our tensile stress is equal to force over area. And then I explained that strain, I'm using S for that, is equal to extension over original length. So you want to take note of this equation. Let's call this equation 3. Let's call this equation what? 4. Stress here, which is force over area. Force is in Newton. Area is in square meter. So we can always have this in mind that the unit of stress is going to be force in Newton per square meter for area. And then, of course, strain has no unit. Strain has no unit. It is a dimensionless quantity. Take note of that. If this is the case, the unit of Young modulus is going to be the unit of stress. The unit of Young modulus is going to be the unit of stress. Why? Look at this. Stress is Newton per square meter. Of course, by the way, I want to say this. That quantity stress dimensionally is the same as pressure, because pressure is also force over area. The pressure you applied on that elastic material. Are you following, right? So it's the same as stress, don't forget. Now, Young modulus is stress over strain. If strain has no unit and stress has the unit of Newton per square meter, it simply means that the unit of Young modulus is going to be the unit of stress, which is Newton per square meter. So dimensionally, they are the same. Let me indicate it here. Unit is still Newton per square meter, unit of Young modulus. Alright, having established this fact, I'd like us to move on still to play around with this equation. I can actually substitute force over area for stress, extension of original length for strain. Let's do that and see what we are going to get. From equation 1, this is going to give us that Young modulus is equal to that equation 1 or equation 2. Equation 2, okay, Young modulus is equal to, in place of tensile stress, I'm going to fix force over what? Over area. We're going to divide that by the strain, and strain is extension over original length. Extension over what? Original length. And of course, we can call this equation 5. This is equal to, should I call this equation 5? How about I call it equation 2a? Okay, let's call it equation 2a so that we know we actually obtained it from equation 2 by fixing equation 3 and 4 in equation 2. Now let us move on. I can simplify this fraction. You know, the numerator is a fraction, force over area. The denominator is a fraction, extension over original length. You can actually do some form of further simplification, division of fraction. And that's going to give us force times the original length. This original length, which is denominator here, will go up. This area will come down to multiply the extension below. So this equation can still be written in this format. So this we can call equation 2b. It's still the same thing as this equation. Still the same as what we have in equation 2. Alright, I hope you understand these equations established and the concept of Young modulus. Take note, our Young modulus here is this capital E. That's the symbol I used for it. Then F, as usual, is force. LO is our original length. A is the area. Then E is extension. I would like you to take note of this, please, about area. Okay, very important. Note, area is equal to length times breadth. It could also be length times thickness. So usually, if questions are given, sometimes an area, the cross-sectional area is not given straightforward, you know. You can be given the length, the breadth of the material. You can be given the length and the thickness of the material. Once you know the length and the thickness, you can actually determine the area of that material so that you use it to solve any problem you asked, okay, as the case might be. Because we are going to prepare for questions to see how likely exam questions on this can be given. I'd like to quickly say this from equation 1. One can plot this tensile stress against tensile strain. If you plot tensile stress against tensile strain, the slope of that graph is going to be Young modulus. Let me just show that here quickly. Now let's say we have a graph of stress against strain. Stress against strain. Now you're going to get a straight line, okay, which expectedly will pass through the origin. Okay, you get something like this. Then if you take the slope, look at it. The slope is going to be equal to Young modulus. Slope is equal to Young modulus. You want to take note of that. If you plot stress against strain, an examiner can test you on this, okay? Right, this is pretty cool. I hope you enjoyed it, right? If you're yet to subscribe to the GMAT 41 YouTube channel, please do that, okay? Kindly hit the subscription button, turn on the notification bell, personalize it so that once I upload any new content, you will be personally notified. Let us pick some exam-related questions and this and see how we handle them. And here we've got our first question. A force of 500 Newton is applied to a steel wire of cross-sectional area 0.2 square meter. The tensile stress is, so how do we obtain the tensile stress of this steel wire? Now, if you look at the question, the force was given to us to be equal to 500 Newton. And of course, we're given the cross-sectional area, simply area of the steel wire is given to be 0.2 square meter. Because very simple, we're asked to calculate the stress. I'm using this symbol to represent stress. So what do we do there? Simply recall that stress is equal to force divided by area. And that's going to give us that stress is equal to 500 divided by the area is 0.2. Now, how do you solve this assuming there is no calculator available? As long as you have a decimal number here, convert the terms you have there to whole number as much as possible. Now looking at this is 0.2. You have only one decimal digit there, and that's the only decimal digits that you have there. 0.2, just one. So for that reason, you multiply the numerator and denominator by 10. Doing that, it means that this is the same as 5,000 divided by 2. Multiply 500 by 10, you get 5,000. 0.2 by 10, you get 2. So that with this, I can now reduce the whole number. And of course, doing this division, you are going to get, if this goes into 5, that's 2 remainder 1. Attach the 1 to this 0, you get 10. 2 divide 10, you get 5. So this is actually going to be 2,500 Newton per square meter, or you can still write as Newton, then meter raised to power minus 2. So 2,500 is our what? Tensile stress. In standard form, we can still write this as 2.5 times 10 to the power of what? 3 Newton per square meter. Of course, this is the value of the tensile stress. Looking at the option, what do we have as the correct option? That goes with option D. And now, our second question. Question number 2. A copper wire was subjected to a tensile stress of 7.7 times 10 to the power of 7 Newton per square meter. Calculate the tensile strain of the wire. Now we're giving Young modulus to be equal to 1.1 times 10 to the 11th power times 10 to the power of 11, okay? Newton per square meter. We've got our options as usual. Now, how do we obtain our tensile strain in this case? Remember, the examiner has given us tensile stress. So I want to declare my data to bring out the information I know. Tensile stress was given as 7.7 times 10 to the power of 7 Newton per square meter. By the way, let me say this place. When seated, let's assume JAMB exam specifically. Do you really need to bring out this data, this information? Do you need to declare them? You don't need that. And for any CBT exam objective, here you have options provided. Okay, you can just start solving straight. Once you know the formula that can solve the question, just write out the formula and then start applying. You don't even need to even write the formula if you don't want to. Let us assume, like in this case, the tensile stress is this. Now I was asked to calculate the tensile strain. Young modulus was given to me. Now I know generally from what we've established already that stress is equal to Young modulus times strain, which means that strain will be stress over Young modulus. So with that idea, all I will just do is simply strain equal to 7.7 times 10 to the power of 7 divided by the Young modulus, 1.1. times 10 to the power of 11. Okay, I would like to say that what I usually do by declaring my data, the information given, is just for you to understand the full approach to dealing with this. There are strategies we use in solving calculation problems. First of all, you want to get to know the data, the information, the parameters given to you in the question. Okay, then you don't think the formula that can solve the information given. Are you following right? The formula that connects the data, the parameters given, and you solve. And then for the sake of those that are sitting for theory exams, where you need to express yourself on paper, all right, you show your workings and other things. That's why usually I present my information, the data, before thinking of the formula and solving, okay? If it is JAMB directly, you have the formula, you can just start solving. All right, so we move on. The next, we're giving Young modulus. I use E for that, 1.1 times 10 to the power of 11 Newton per square meter. Strain S is equal to stress divided by Young modulus. Substituting, we are going to get, now we could decide to convert this 7.7 and 1.1 to a whole number, of course, without calculator. That's the fastest thing to do. Likely, each of them is one decimal. So since you have one decimal digit there as the highest number of decimal digits, all we just have to do is to multiply each of them by 10. If you multiply this by 10, you get 77. This by 10, you get 11. 77 divided by 11 is going to give us 7. So this becomes 7 times 10 to the power of. Now we can work out this using the knowledge of indices. It's going to be 7, then 11 will go up to become minus 11. 7 minus 11 is going to give us minus 4. Remember that strain has no unit. Tensile strain has no unit. So this is our answer. And of course, having done that, if you look at the option provided, the correct answer is option A. And I hope you love this, right? Okay, let us take our next question, number 3. Question number 3 reads, the tendon in a man's leg is 0.01 meter long. If a force of 5 newtons stretches the tendon by 2.0 times 10 to the power of minus 5 meter, calculate the strain on the muscle. Have you ever experienced muscle strain before? Muscle pull. Some kind of force must have acted on your tendon, okay, to stretch it, and you feel that muscle pain there, okay? We refer to it as muscle pull. So this is just a kind of applied question to our body, and the examiner asks us to calculate the strain on the muscle. Now, I do not want us to declare our data anymore, like bringing out the parameters, the values given to us, this, what do they represent? I don't want us to write it out. We have them in our brain already. We can read and understand this. And I think that is sufficient in an objective case to deal with the question without declaring your data. From the question here, the tendon, the length is 0.01 meter. So we know the original length of the tendon. And now the force was given to us to be 5 Newton, which stretched the tendon by 2.0 times 10 to the power of minus 5. The use of the word by means that you've been given the extension. I already explained this, I guess, in part 2 of extension. Of course, you can actually click the info link here in order to go to part 2 of Hooke's law of elasticity, where we treated, calculation on part 1. All right. So we know the extension here already, and we're asked to calculate the strain. Once we know extension, we know original length of that material, we are good to go. Strain is equal to extension over what? Original length. Solving this, we have that strain is 2.0 times 10 to the power of minus 5. We are dividing it by the original length, which is 0.01 meter given. And simplifying this, convert to whole numbers, okay, using the highest decimal digits part. If you look at 2.0, this is just a whole number 2, this is 0.01. How many decimal digits do we have here? 2, 0, 1, is that not so? So you're going to multiply these 2 and 0.01 by 100. We have 2 decimal digits here. 100 has 2 zeros in it, okay? So that's the idea. If it is 1 decimal digit, you multiply by 10, which has 1 zero. If it is 2 decimal digits, you multiply by 100, which has 2 zeros. So let me ask you, if it is a 3 decimal digit number, you multiply by what? By 1000. Okay, so that's the guide. Like I said, the GMAT 41's basic math class can help you to handle all these basic arithmetics. And I am glad to inform you that the GMAT 41 has formally launched the GMAT 41's basic class YouTube channel. In the description box of this video lesson and in the comment box just below this video lesson, you will find a link to the GMAT 41's basic class channel. It can also help you remember every advanced stuff we learn from senior class, SS1, 2, 3, preparing for JAMB as the case might be, advanced level, 100 level, 200 level and above. Whatever you learn in this level of education are built on your basic knowledge. So you want to take your basic level of knowledge very seriously. Now let us move on. If I multiply this 2.0 by 100, I'm going to get 200, then times 10 to the power of minus 5. Multiply this 0.01 by 100 is going to give me 1. So you see that the strain is now 200 divided by 1, which is the same as 200 times 10 to the power of minus 5. Standardizing this, okay? Writing it in basic standard form. You know that this 200 can't be left in this form. Decimal point you have to move, because normally if you have 200 there is an invisible decimal point after the last zero here. So what do? You move the point 2 times 1 and what? 2. So that's going to give us 2.00 times 10 to the power of. I move the point 2 times to the left. Since I moved to the left, I'm going to add that 2 to minus 5, which is the power of 10 here. If you move to the right, you are expected to subtract the number of times you moved the point. Subtract it from the power of 10. So in this case, we move to the left 2 times. So I'm going to add 2 to minus 5. And if you add 2 to minus 5, you're going to get minus 3. And of course, this is the result. Okay, 2.00 is the same as 2.0. Are you following, right? Times 10 to the power of minus 3. Coming back to this, the correct option is going to be option C. 2 times 10 to the power of minus 3. And I hope you enjoyed this part 3 of elasticity and Hooke's law, having learned the concept of Young modulus. Please share these video lessons to your friends, to other scholars. Alright? Like I've always said, these are concepts that are needed. Whether you are in SS1, 2, 3, whether you are preparing for your WAEC, whether you are taking JAMB, whether you are an undergraduate, 100 level, 200 level, as the case might be, you need this video lesson. So share this video to all the scholars so that they can get access to it and benefit from it. In our next physics class, I'll be taking you on projectile motion. You will not want to miss that class, right? So if you are yet to subscribe, please kindly subscribe, hit the subscription button, turn on the notification bell and personalize your subscription so that once I upload that content and any other one, you'll be personally notified. Remember, from here at GMAT 41, think physics, think chemistry, think maths. At any level, we are here to give you the best that you deserve. Always take your studies seriously. See you in our next class.